All right, welcome everyone. Today, we're going to dive into the really cool world of number theory. This is all about the hidden rules that govern the integers all around us. You know, it's this fascinating area of math where really simple questions can lead to some incredibly deep and complex answers.
So, let's just jump right in with a puzzle. Take a look at this equation. Now, finding solutions with any old real number, not too hard. But finding integer solutions, well, this exact problem stumped the best mathematicians for over 60 years. It's the perfect example of what number theory is all about, exploring the surprisingly deep, often tricky properties of plain old whole numbers. Okay, so here's the game plan for today. We're going to start with the absolute fundamentals, the building blocks of numbers. And from there, we'll build our way up to some really powerful theorems that are honestly key to mastering this subject.
So first things first, we've got to talk about prime numbers. The best way to think about them is as the atoms of mathematics. They really are the fundamental particles that every other whole number is built from.
Before we go any further, just a super quick refresher on a term we're going to be using a lot, a factor. A factor is just any number that divides another number perfectly, with zero remainder. So for 24, you've got a whole bunch of them. 1, 2, 3, 4, and so on, all the way up to 24 itself. Simple enough, right? Okay, so a prime number. This is a number that you just can't break down any further. Its only factors are 1 and itself. That's it. That makes it a fundamental unit, one of those indivisible atoms we were just talking about. And this brings us to one of the most important ideas in all of math, the fundamental theorem of arithmetic. It basically says that every single integer can be written as a unique product of primes. It's like a chemical formula or a DNA sequence just for that number. Take 84. It's always going to be 2 squared times 3 times 7. No other combo of primes will ever give you 84. It's unique. Now, once you have that prime factorization, you can do some amazing things. Like, you can instantly figure out the total number of factors a number has. Instead of sitting there trying to list them all out, you just take the exponents from its prime factorization, add 1 to each of them, and then multiply those new numbers together. So for 84, that's just 2 plus 1 times 1 plus 1 times 1 plus 1, which gives us 12. This is a huge time saver on an exam. And, believe it or not, it doesn't stop there. With that prime factorization, you unlock the ability to calculate the sum of all the factors and even the product of all the factors using these incredibly powerful formulas. Seriously, think of these as amazing shortcuts for problems that would otherwise be a total nightmare to solve. Okay, so now let's take all that and see how we can actually use it in some really essential algorithms. These are the powerful tools that let us solve problems efficiently, not just on exams, but in things like computer science too. First up, we have the sieve of Eratosthenes. It's just a brilliant and super efficient way to find all the prime numbers up to a certain point. Just imagine you have a big list of numbers. You start with 2, which you know is prime, and you cross out every multiple of 2. Then you go to the next number that isn't crossed out. That's 3, and you cross out all of its multiples. You just keep doing that, and the numbers left standing at the end, those are your primes.
Now, before we get to our next big algorithm, we need to make sure we're clear on 2 really important ideas, GCD and LCM. The greatest common divisor, or GCD, is pretty self-explanatory. It's the biggest number that divides both of your integers. And the least common multiple, or LCM, is the smallest number that both of your integers divide into. So for 24 and 36, their GCD is 12, and their LCM is 72.
Okay, that brings us to Euclid's algorithm. This thing is ancient, but it's one of the fastest algorithms ever for finding the GCD. The logic is so elegant. The GCD of 2 numbers A and B is the exact same as the GCD of B and the remainder you get when you divide A by B. You just keep repeating that little trick until your remainder hits 0.
Let's watch it work. To get the GCD of 36 and 24, we find the remainder of 36 divided by 24. That's 12. So now our problem is finding the GCD of 24 and 12. Well, 24 divided by 12 has a remainder of 0. And since we hit a remainder of 0, the algorithm stops. The answer is the other number, 12. See? Incredibly fast.
All right, let's totally shift gears and dive into a different way of looking at numbers, modular arithmetic. This is all about remainders and cycles. It might sound a bit weird at first, but it has applications literally everywhere, from modern cryptography to computer science.
So, to really get a feel for this, let me ask you a question. What does a regular 12-hour clock have in common with computer programming? The answer is they both use a system where numbers wrap around. On a clock, after 12 o'clock, you're back at 1. In computers, numbers do the same thing when they get too big. That wrapping around idea, that is the soul of modular arithmetic. And here's the core idea. I like to call it clock math. You pick a number, which we call the modulus, and from then on, you only care about the remainder when other numbers are divided by it. So for example, if we're working with a modulus of 17, then the number 75 is basically the same thing as the number 7, because 75 divided by 17 leaves a remainder of 7.
Now what's really cool about this is that we can still do all our normal math, addition, subtraction, multiplication, but we get to do it with the much smaller remainders instead of the giant original numbers. This is a massive advantage because it keeps our calculations from getting out of control. We can just take the modulus at every single step to keep things small.
So for our last section, we're going to look at some really powerful theorems that tie all of these ideas together. This is where you see the real problem-solving punch of number theory, especially when it comes to tackling the kinds of tough problems you might see on an exam.
First, we need to get familiar with a tool called Euler's totient function. It looks like this, phi of n. So what does it do? It counts how many numbers from 1 up to n are co-prime to n. Now, what does co-prime mean? It just means their greatest common divisor is 1. They share no common factors other than 1. And here's a handy shortcut. For any prime number p, its totient, phi of p, is just p minus 1. This little function is the key to our next big theorem. And that brings us to Euler's theorem. This thing is an absolute game changer. It says that if you take a number a and raise it to the power of phi of m, the result modulo m is always 1, as long as a and m are co-prime. This is the secret weapon for taming massive exponents in modular arithmetic.
And what's super cool is that Euler's theorem also gives us a way to do division in this modular world using something called a modular inverse. The inverse of a is just some number that when you multiply it by a, you get 1 in that modulus. And look at that! We have a direct formula to find it, and it uses that very same totient function.
Okay, let's put these tools to work on a classic problem, the linear Diophantine equation. Here's how you should think it through. Step 1. Check if a solution even exists. It only does if C is divisible by the GCD of A and B. If it is, great. Step 2. Use a beefed-up version of Euclid's algorithm to find one initial solution. And then, once you have that one solution, you can use a formula to generate every other possible solution. To wrap this all up, here are the absolute must-knows for your revision. First, master prime factorization. It is the foundation for almost everything else. Second, understand why Euclid's algorithm works. Don't just memorize the steps. And finally, always remember that crucial condition for Euler's theorem. The numbers have to be co-prime. Get these concepts down cold and you'll be in great shape.
And I'll leave you with this final thought. All of modern digital security, the stuff that protects your bank account, your emails, everything, is built on the fact that one of the problems we talked about today is incredibly hard to solve for very, very large numbers. Just think about that. These abstract ideas we've been exploring are literally the bedrock of our modern digital world. It just goes to show you the incredible power of number theory.